Today I'll be talking about NVIDIA's Jetson Platform and how you can use it to build and deploy AI-enabled autonomous machines at scale. I hope you enjoyed seeing the video and got a sense of what you're going to learn about today. Let's first understand what is driving the growth of AI at the edge. The improvement in sensor technology and economics has created a boom of connected devices, also known as the Internet of Things. These devices are making productivity improvements and enabling use cases that were previously not possible, such as autonomous mobile robots for warehouses and last-mile delivery, voice and perception-enabled assistants, smart and safe cities, and predictive maintenance. Several of these devices need AI at the edge because of one of the four reasons. First, they either generate a huge amount of data, making it prohibitive to stream to the cloud for processing. Second, they are operating in environments where reliable connectivity is not guaranteed. Third, they need to act in real time and take control and cannot tolerate the latency of cloud. And fourth is that the data cannot leave the device for a lot of these applications because of the privacy reasons. The number of IoT devices are growing exponentially, with forecasts estimating 150 billion devices by 2025 and over 1 trillion devices by 2030, presenting a huge opportunity for AI at the edge. As we see companies building and deploying solutions for AI at the edge, we are learning about a lot of unique challenges that are very different from a traditional embedded computing system and requires a fundamentally new approach of development and deployment. So let's look at some of these challenges. The first challenge is that the growing diversity and complexity of neural network models. Due to the rapid advancements in the field of AI, we see new model architectures emerging almost every day. And to keep up with this fast pace of innovation, it is important that you choose a computing platform that is flexible to support the models of today and is prepared to support the models of tomorrow. The second challenge is that inference is usually a piece of complex application pipeline, and building a compelling solution requires accelerating the full stack. We often see companies choosing an architecture where they use an accelerator for the AI part of the pipeline, but quickly realize that the functions before and after inference become the bottleneck, as they are limited by Amdahl's law. Therefore, it is important to accelerate the entire pipeline and not just the AI algorithm. And lastly, since AI devices are essentially software-defined systems that get better over time as they gather more training data, they need to be connected, monitored, and updated regularly. Therefore, it's important to have modern DevOps tools and workflows to scale a solution from a handful of devices in pilots to thousands in production. As discussed in the last slide, the complexity and accuracy of AI models is rapidly evolving. The slide helps you visualize that explosion with some of the popular and widely used models. In the left chart, you can see that in just over 5 years, the model complexity has increased by orders of magnitude, with newer models like BERT for NLP have 340 million parameters, and GPT-2 8B has 8.3 billion parameters. Compare that to the early image classification models such as GoogleNet that had just 6.7 million parameters. On the right, you can see various computer vision models, their accuracy, and the compute requirements. Again, we see a large variety of models and solutions that are reaching even superhuman level of accuracy in some cases. To address this growing market of AI at the edge and to solve the various challenges that I just mentioned, we created the Jetson Platform. NVIDIA's Jetson Platform is designed for creating software-defined autonomous machines. It's an open platform that has been widely adopted with over 450,000 registered developers and growing. The Jetson program platform comprises of three main pillars. The first pillar that forms the foundation of our platform is a CUDA GPU-enabled Jetson Computer. The second pillar is the extensive software tools, SDKs, and libraries. And the last pillar is our ecosystem. We'll cover each of these in detail in the following slides. Let's start first with the Jetson Computer. The Jetson Computer comes as a system and module designed from the ground up with high-performance NVIDIA SoC and with embedded GPU for compute, IOs, and memory required to build products with AI at the edge. They come in various power, performance, and form factors to cover a wide variety of applications. The most important thing about the Jetson modules is that they all have the same software architecture, enabling you to leverage your software investment across different product portfolios. At the entry level, we have Jetson Nano, which offers half a teraflop of performance and operates in as little as 5 watts of power, ideal for designing solutions that require processing a couple of models and sensors. On the highest end, we have the Jetson AGX Xavier, which offers 30 trillion operations per second of DL compute in 30 watts for designing complex, fully autonomous systems such as outdoor delivery robots, which require running several models for perception and control in real time and processing high bandwidth data from several sensors. The newest member of the Jetson family is the Jetson Xavier NX. Smaller than a business card, 20 trillion operations per second of AI performance, and just 15 watts of power makes Xavier NX the smallest and most powerful supercomputer for AI available today in the market. The combination of its small size and high performance is enabling a wide variety of applications, such as portable medical devices, autonomous drones, and automated optical inspection systems. As I mentioned before, Jetson is designed from the ground up for autonomous machines and hence offers a lot more than just an AI accelerator. You can see here the various subsystems available in the Jetson AGX Xavier. It includes an easily programmable CUDA-enabled GPU that can also be used for graphics or other accelerated computing functions. There is Tensor cores for AI processing and a deep learning accelerator focused on providing high efficiency convolutional operations for deep learning. There is also a high performance multi-core ARM CPU for all your serial tasks, a multimedia processor for functions such as encoding, decoding, scaling, resizing, and color conversion. We have an image processor for processing the raw pixel data from the image sensors, a vision processor for common computer vision tasks, and high-speed I/Os such as USB, Ethernet, and PCIe. And connecting all of these processors is the unified memory architecture, which truly enables parallel processing with minimal latency and maximum throughput. In addition to the system and modules, we also offer developer kits that bring out most widely used I/Os, and these operate as standalone Linux computers. They can be ordered directly from NVIDIA's website or e-tailers around the world. The second pillar of the Jetson platform is the extensive software stack. Let's look at the different components of that software in detail. Jetpack is the foundational comprehensive SDK that includes everything that you need to start developing on Jetson. It includes an Ubuntu-based Linux operating system that is provided along with a complete kernel source and tools for enabling going to production with things like fusing, encryption, and secure boot. To attach the various sensor and peripherals, it includes drivers for commonly used I/Os such as PCIe, SPI, I2S, I2C, MIPI CSI, and more. For multimedia processing, using the onboard hardware accelerators that I mentioned earlier, we provide common APIs for tasks such as encoding and decoding for various formats and scaling and format conversion. For graphics, we provide support for Vulkan and OpenGL, and X11, Wayland, LibDRM are supported for display. Built on the underlying CUDA-X stack, we provide libraries for deep learning, such as Tensor RT and cuDNN, libraries for computer vision, such as VisionWorks, and other fundamental accelerated computing libraries, such as cuBLAS and cuA50. Another key component of Jetpack is the development tools that run on the host and enable developers to cross-compile, profile, and debug their application. Providing all the key components together as a single SDK really makes the developer's life easy and makes it easy for them to develop and go to production fast without having to spend a lot of time resolving dependencies and putting the tools together. NVIDIA's Tensor RT is one of the key libraries for AI that's included in Jetpack and supported on Jetson. Tensor RT includes a compiler and a runtime that allows developers to bring their models trained on any of the popular AI frameworks such as Tensorflow and PyTorch and deployment on the edge with minimal memory footprint and providing highest performance leveraging the underlying architecture of the product. Tensor RT takes care of tasks like quantization, layer fusion, kernel auto-tuning, multi-stream execution, and more, so that developers can quickly go from training their models to deploying them on the edge without having to jump a lot of hoops, understanding what they need to do to optimize it. The seamless workflow from training to inference enabled by NVIDIA's unified architecture is extremely critical to the success of AI projects due to the inherently iterative nature of the development and deployment process of AI projects. This chart shows some of the data highlighting the capabilities of Tensor RT. We run a diverse set of benchmark models for classification, detection, pose estimation, segmentation, image enhancement, and even models like BERT for natural language processing can all be accelerated and run in real time with Tensor RT running on the edge with Jetson. These models were trained with different frameworks. They have different neural network architectures, but they all can be compiled and run on the same Jetson device with Tensor RT. While these benchmarks are great to understand the compute capability of our platform and its flexibility, they are far from sufficient to choose the right platform for your product. So let me go and explain why you need to look beyond the benchmarks when choosing a product for your practical application. AI inference is fundamentally a multidimensional problem. The first dimension is the type of model. As we saw earlier, the research in AI is progressing rapidly, and we see new model architectures emerging frequently. If you choose a model today, it is most likely that in 6 months you will want to update with something different that offers better accuracy and performance. Hence, it's important to choose a platform that can accelerate every model. Second dimension is the input resolution. The benchmarks you saw earlier often show the performance for very small resolution inputs, and that were used for ImageNet Challenge or other academic research. But in practice, you need to iterate and explore what input resolution will work for your problem. For example, you cannot detect a sub-millimeter manufacturing defect if you scale your input to a 224 by 224 resolution, which is what was used by a lot of benchmarks. The third is the choice of framework. The biggest challenge today for companies developing AI projects is finding AI developers. So if you limit your solution to a specific framework, you're going to close the doors to a huge talent pool. Fourth is the batch size or stream processing. For many use cases, you need to process more than one sensor, more than one input, and the benchmarks show great performance for a single input. But when you add more inputs, the performance does not split across evenly. And the last one is quantization. While it can really help reduce the compute needs, it often requires a lot of effort and is not feasible for many cases. One example for this is a customer who needed to distinguish a weed from the crops, and given the minute feature differences, they absolutely had to use floating point 32 to get the desired accuracy. So having the flexibility to iterate across these multiple dimensions is important, and with Jetson and NVIDIA platform, you have the flexibility to explore and iterate across all these dimensions to build the best product in the shortest time. The flexibility of the Jetson platform was also exhibited in the latest ML4 inference benchmark that was published recently. ML4 is a third-party benchmark where almost all commercially available solutions for AI competed, and Jetson topped the performance across a wide variety of workloads and scenarios. In fact, Jetson was the only platform that could even run all the scenarios and workloads in the edge and mobile SoCs category. An important thing to notice here is that even though we topped the ResNet 50 offline performance with 2,158 images per second, it is practically useless for anybody trying to choose a platform because there is no edge device that needs that performance at that resolution. However, what is important is that due to the flexibility and programmability of our architecture, we are able to translate that performance to more practical scenarios, like the real-time object detection for a 1200 by 1200 resolution input, which is a very practical and important use case for autonomous vehicles that need to look far out and need a higher resolution input and more pixels to detect a person or an object far away. So that capability to translate the performance across the different scenarios, across the different model types, is extremely important for when you start to deploy AI in practice. For anyone interested in digging deeper, all the source code and the results of this benchmark are publicly available on the ML4 GitHub. Coming back to the Jetson software, as we discussed, one of the challenges of deploying AI at the edge is that accelerating the inference alone is not enough, and we need to accelerate the full pipeline to achieve the performance goals. Built on top of the Jetpack SDK, we have the DeepStream SDK. DeepStream was designed to accelerate the full stack required for streaming video analytics. It's a modular SDK that allows developers to build a highly efficient pipeline for intelligent video analytics, or IVA. What you see here is a typical IVA pipeline constructed with DeepStream plugins, and at the bottom, it shows the underlying hardware that is used by the plugin. By accelerating each function of the pipeline and leveraging the hardware architecture to move the data without any memory copy, we are able to achieve up to 5x throughput of what one would get if you were accelerating only the inference. Several of our customers have successfully used this SDK for analyzing data from smart cities, building perception for robots, and customer analytics for retail. For a deep dive on DeepStream, please remember to watch session 22100 from my colleague Chintan that was presented also in Digital GTC. Similar to DeepStream, we have created Isaac SDK for robotics. Isaac includes an engine that lets you build your complex application graph in a modular way and includes a variety of gems that provide common algorithms and AI functions required to build mobile robots and tools for visualizing and debugging. The different gems are mapped to the different appropriate hardware on the system for acceleration, and the engine enables efficient data flow. What you see here is a graph of one of the sample applications that we provide with Isaac called Carter. It uses various gems such as localization, mapping, obstacle avoidance, path planning to build an autonomous indoor mobile robot. So to summarize, the Jetson platform comes with an exhaustive set of software that enables easy and fast development of AI-enabled applications for smart cities, factories, logistics, healthcare, agriculture, and more. Since Jetson is used to build software-defined autonomous machines, we regularly ship new software releases that bring new capabilities, new features, and higher performance to the Jetson portfolio. These releases come out roughly about every 6 months. In this slide, you can see the major software releases since Jetson TX1 was announced. Here is a fun fact. While most devices tend to get slower over time, we, on the contrary, have almost doubled the AI performance of TX1 with just software updates in the 3 years since it was launched in 2016. And this has only been possible because of our unified software architecture and a huge investment in AI. The third and the last pillar of the Jetson platform is our ecosystem. Our ecosystem partners are a vital piece of our platform as they provide support to our customers every step of the way to enable faster time to market. Whether you need an off-the-shelf system for initial prototyping or a custom design for mass production, our ecosystem partners can help you. As you can see from some of the logos here, our ecosystem spans across a wide variety of functions and regions. In addition to the sensor and hardware partners, we also have an extensive software ecosystem that includes ISVs that can provide AI solutions for specific verticals, cloud service providers that provide cloud integration, device management, and monitoring solutions, and other partners that provide custom optimization and integration services for embedded systems. Finally, we have our distribution partners to enable global supply chain and also provide local FAE support to our customers. The depth and breadth of our ecosystem is a big reason why our customers are able to develop and deploy complex products to the market in record time. Building on the 3 pillars of the Jetson platform, we are seeing a huge success in deployment of AI solutions at the edge across a wide variety of use cases and industries, some of which are shown here. These solutions are not only helping our industries to be more productive, but also making our world safer, healthier, and happier. Given the current times, I would like to call out a few of them. TX2 is being used by its company Nano4 to perform DNA sequencing in the field. Delivery robots like JDX are using Jetson Xavier to provide supplies in areas of quarantine and service robots are lending a hand to patients and doctors in hospitals. And a demonstration of some of this success was shown in the video that was broadcasted earlier in this talk. We have made a huge investment in our Jetson portfolio and have a solid roadmap of products planned for the future. All products in green are available or announced today. Looking out into the future, in 2021, we are planning a Nano next for the entry level, which will be followed by the Orin-based products for both mainstream and the top end in 2022. These are all in planning stages and subject to change. Similar to the commercial SKUs, we plan to continue delivering products for the industrial environment, which require high reliability, operating life, and supply for up to 10 years. Following TX2i, we are planning to launch the industrial version of AGX Xavier in middle of 2021, followed by Orion Industrial after 2022. So Jetson has been adopted very widely from a wide spectrum of developers, ranging from high schools to startups to Fortune 500 companies. And this has been possible because it's an open platform with a lot of resources to learn and create. You can order the developer kits from NVIDIA.com or retailers around the world. There are dozens of high-quality open source projects that have been created both by NVIDIA and our developer community. These projects provide you a springboard to jumpstart your development. The Jetson Forum is a key resource where NVIDIA's dedicated technical team, along with the ecosystem partners and the community, provide you answers to your questions and share the experiences. The DLI and the GTC also provide opportunities for completing courses and workshops to advance your learning on AI. So with that, I would like to thank you all for attending this talk today and for being a part of CTSA Digital. And we will now open up the line for any Q&As. The question on expansion of teraflops, that stands for trillion floating operations per second, the number of trillion operations per second. There was a question on the teraops for Nano for int8. Nano only supports floating point 16, so it does not support int8. There was another question on what is kernel auto-tuning. So if you're familiar with the way GPU and the CUDA architecture works in terms of accelerating performance, you have to create kernels to automate for acceleration. And depending on your model architecture and the layers and also the GPU architecture that you're running on, there are different kernels that can be created to accelerate the model. So what Tensor RT does is looks at your model, looks at the underlying GPU architecture, and does an automatic calculation of what will be the best kernel to give you the maximum performance for that particular model. There's a question about what is the complete system like this cost range. It's not clear what system you're talking about, but if you look at our developer kits, the Jetson Nano is available for $100, and the Jetson AGX Xavier retails for $700 US. There's a question on when the NX module is going to be available. We are targeting middle to end of April, so sometime next month for NX module to be made available. There's a question which says, since it's getting more and more complex, how do you keep the overview? Well, the good thing about the Jetson platform is that it's all a unified software architecture. It's all a software-defined system. So any time that you're spending in learning and building your expertise with the current generation of products and software, it will naturally translate to the next product. So there is no new learning to be done as new complex solutions continue to come to market. Is the new Jetson Xavier available as a developer kit? At this point, we have only announced the module for the Jetson Xavier NX, and it is compatible with the Jetson Nano developer kit. There's a question on which one of the deep learning development environments are better suited for Tensor RT, Tensorflow, PyTorch, or something else. Well, as I mentioned, the beauty of the Jetson and NVIDIA platform is that we support every single framework that is used today across the industry. And within these frameworks, there is some level of standardization that is happening where they're all trying to converge to Onyx as a format for exporting. So we see that becoming more and more of a norm, and we are continuing to invest in that space. But to answer your question, you choose the platform that you are most familiar with, whether it's TensorFlow or PyTorch, and we will provide deployment for that on the edge. There was a question on what are these numbers, FPS. I assume this was the question for the benchmark chart that I had shown. And yes, for all the image benchmarks, the number was in FPS. And we had two charts for natural language processing, and that was the latency of the query for the NLP algorithm. There's a question, what circuits are available for Jetson Nano? I'll need some more insight into what that means, so we'll reserve that for later. What was the session number of the Deep Stream Deep Dive? Let me quickly...
You don't have to worry about that one. You can keep it to this topic.
There's a question if there are any hardware vendors that have 5G modem support for the Nano. If you look at our ecosystem partners, and go to our webpage, there are several hardware ecosystem partners that have been identified, and I believe there are a few of them that have 5G modem support for the Nano carrier board. There was a question on which type of smart city. We have a project with Verizon, for example, that has been publicly discussed, and it's being deployed in Europe and in some places in the US, where they're now using, understanding the occupancy, and based on that, doing smart lighting. And as you can imagine, there are a large period of time when there's nobody on the road. And so keeping the lights on when there is no activity, there's nobody, is a huge cost for the city. So the solutions like this and traffic monitoring solutions, understanding the traffic flow based on that, controlling the red lights and designing the intersection is another area that's being explored in pretty much every country at this point. How long or years given Jetson module receives new update from NVIDIA, for instance, new firmware for Ubuntu? Well, in terms of new updates, as I mentioned, Jetson TX1 was launched in 2016, and we did make an update up to 2019 for the TX1. And we make a decision based on where our customers are in terms of their life cycle, and based on that, decide whether it makes sense to do a new update or what level of updates are needed. But as you can see, we've been doing releasing updates for TX1 till up to 2019. Can you talk about any applications for Tiny YOLO? Well, there's a lot of applications for Tiny YOLO based object detection, whether it's robots trying to identify obstacle in its way, or whether it's smart, traffic camera trying to count the number of cars. It's been used in a wide variety of applications. Again, there's a question on availability of Jetson NX, and for those of you who missed it, it's again targeted for April, mid-April, end of April. On Jetson Nano, with encoding 4K 30 frames per second video stream take close to 10 watts or 5 watts. If you're just doing a 4K 30 encoding, I would expect that to be more in the 5 watt range. On Jetson Nano, what is the difference in the peak FP16 flops between 10 watts and 5 watts operation? So the 10 watts operation provides about half a teraflop, and at 5 watts, you get roughly close to 70% of that performance. There's a question about the energy consumption of Jetson product. So that's a good question, and one that I would like to take a couple of minutes to explain. So when we talk about the Jetson products and the power consumption, we take into account the entire computer. It's the SoC, it's the power management, it's the DRAM, it's the IOs, all of it put together. And if you compare it to an accelerator or another chip-only solution, the power number that you see there is for a particular rail or a particular IP within that entire complex system. So, for example, if you look at Jetson Nano, which is a 5 to 10 watt product, and if you looked at how much power is consumed by the GPU alone, it would be more like 2 to 3 watts. So they are inherently very power efficient. Going into Xavier, we have also introduced DLA, which is again a highly efficient accelerator for deep learning. So with Jetson, the power that we mentioned as a product is the full system power. But if you go down and look into the details, every IP is power optimized. So I don't see that to be a problem with most of our customers once they understand what is the true power of each of those IPs and what the system level power is. Is there support for Google environmental sensor on Jetson Nano? I'll have to go back and check, but I believe if they are interfacing over one of the IOs like I2S or I2C, they could be supported. What is the absolute maximum power usage of TX2s and Xaviers in the max end mode? So there are two things to keep in mind. The power that for TX2 is roughly 15 to 20 watts, and for Xavier it is about 30 watts. And these are the TDP limits. And so when you're running in max end mode, you could easily exceed those, but given the TDP constraints, we don't expect anybody to use more than 30 watts. And another good thing at NVIDIA is we dog food. We use a lot of our products ourselves. We use the Xavier to build robots ourselves, to build self-driving cars. So we also evaluate and understand what is the real requirement. So for most autonomous applications for Xavier, 30 watts is what you should be able to use and get a meaningful performance out of Xavier. Is there a production-ready carrier board for Jetson Nano NX that we can use in production? The ecosystem that I mentioned in my presentation has a huge variety of carrier boards. So then they are available today for Jetson Nano, and as soon as Jetson Xavier NX gets launched, they are all ready to ship production-ready boards for you to go to market really fast. There's a question from on, are there any recommended or supported RTOS for the Jetson lineup? So I've mentioned that in my slides. Starting with the TX2 and AGX Xavier, we do have a dedicated R5 ARM R5 subsystem, and we provide free RTOS that runs on that subsystem. If you're looking for more real-time kind of operating system for the main CPU complex, we have some of our ecosystem partners that I shared. One of our ecosystem partners has a OS called Red Hawk, which provides real-time patches on top of Ubuntu. So it's possible to get some of the real-time capabilities on the BSP that we provide. So I would definitely go and look into Red Hawk if you're interested in RTOS. When can we expect the next Jetson product after Xavier? I guess maybe you missed my slide on the roadmap. We are looking at Orin-based products in 2022. Again, we would have both a mainstream product and a high-end product based on Orin. And in 2021, we are looking at the next version of Jetson Nano. Can you recommend hardware partners for airborne communication for video streaming to ground systems? I would again look at our ecosystem partners and contact them. I know, as I saw in some of these videos, Jetson is being used for a lot of drones and aerial vehicles, and so they have solutions that are being used for streaming of videos for those applications. So definitely check with our ecosystem partners. I'm pretty sure they have something for you. Is NVIDIA looking to support more industrial protocols in L14 native libraries, i.e. Modbus and CIP? This is something that we have thought about, and at this point, our plan is to again let our partners who are serving these particular industries. They have a lot of expertise in this domain, and they are fulfilling these customer needs for Jetson customers. So at this point, we are planning to continue to lean on our partners for providing these protocols on the Jetson products. Okay. How long will the Jetson product be supported? Generally, the GPU is supported for a few years, and it becomes problematic when Jetson products are used for longer. So the Jetson products are designed for the embedded market. So we understand the life cycle of those products have to be longer. So every product in our commercial segment is guaranteed to be available for about 5 years of supply. And if you need further extended lifetime, our distribution partners will be happy to have that conversation with you. We know of other customers who have had this discussion and negotiated agreements to continue to provide end-of-life support through our distribution. But from NVIDIA side, we are committing to 5 years, at least for the commercial product, and a minimum of 10 years for our industrial SKU. Right. What SLAM algorithms does Isaac use? So today, Isaac has two SLAM algorithms. One is using the cartographer SLAM, LiDAR-based SLAM, and then we also have a gem for visual inertial odometry. So you can find the details for that on our Isaac developer page. All the documentation and details of the different algorithms is available there. You mentioned some of the benchmarks are scaled for small size. How would you use limited hardware capability for larger input size? In partitioning and scheduling, the compiler assist. How does partition the multiple GPUs? Yeah. So as I mentioned, the benchmarks that you see often are using very small input resolution, And the reason is that a lot of them have architectural dependencies that the weights have to live within the onboard memory. And however, with Jetson and the GPU architecture, there is no such limitation. As long as you can, you have a model and that can fit into the space for the onboard memory as well as DRAM or the swap, you should be able to process it on Jetson. Your latency that you will see for AI inference will vary, but there is no fundamental architectural limitation that limits you to only process data for certain input size. And that's extremely important, as I mentioned in my presentation, to be able to experiment with that resolution, because what resolution will be able to detect the details that you want is something that you can only arrive at after doing some iterations. Can the Xavier NX and AGX be used for training or just for inference? Well, the short answer is yes, it can be used for training. And the reason being that we are using the same CUDA GPUs that you see in a $100,000 server, DGX server. So the same GPU architecture is available on Jetson, right? So that's the reason you have unlimited capabilities on what you can run, what kind of models can be run. And so you can do training, but of course, it's going to be limited given the amount of compute that's there in terms of the time it takes to train something. However, if you're looking for on-the-fly incremental training, that's something definitely that can be done on the Jetson, and we have seen our partners build solutions around that as well. I've had reports from customers that 16 GB Xavier is no longer available in the US. Is this phased out towards 32 GB? That is correct. Based on since we use our own products and our feedback from customers, we decided to upgrade the memory on the Jetson AGX Xavier from 16 GB to 32 gigabytes. And there's been no change of price associated with this. So essentially, it's just more value for our customers, and they can run more neural networks more easily with the 32 gigabytes of memory now. Comparing to the Jetson Nano, I would like to know if OpenCV performance will be better on the Xavier NX necessarily. Well, OpenCV has a mixed set of functions. So if you're compiling OpenCV with CUDA support, there are some functions that can leverage the onboard GPU, and then there are others that leverage the native ARM instructions for acceleration. Since Xavier NX uses a newer version of ARM, it has more number of ARM CPUs, more frequency, and also new version of GPU, you would expect to see a lot of improvement in performance for OpenCV as you go from Nano to Xavier NX. Will there be 10 gigabit Ethernet support in the future? Yes, I think that's definitely something that we are looking into, and I hope we would be able to add that in the future Jetson products. Does the Tensor RT Compiler require an additional tool chain, or is it standalone? So Tensor RT is, as I mentioned, built on top of CUDA and cuDNN. So it does require you to have CUDA, cuDNN, and beyond that, it's a standalone tool that can be run on the device for compiling and runtime. Why can't Tensor RT support other targets, microcontrollers, and FPGAs? Well, Tensor RT, as I mentioned, does a lot of operations, some of which are possible to be translated across architectures. But as I mentioned in my slides, some of the things like order kernel tuning and layer fusion are things that are done by the compiler, keeping in mind the underlying hardware architecture that it's running on. And so we, of course, understand very well our GPU architectures. So Tensor RT is designed for that reason. How the exploration of the different dimensions we mentioned is possible with Jetpack. So I believe this question is regards to the different dimensions of AI that I mentioned. Well, there's nothing special that you need from Jetpack for that, given that our software libraries are designed and are flexible to support all these different dimensions. You don't need anything additional. Jetpack has everything compensated in it to provide you the ability to explore and iterate with the different dimensions that I mentioned. What's better to focus on learning PyTorch or TensorFlow? Well, whatever you find easy. They're all great, the AI frameworks. You say that Xavier NX is compatible with Jetson Nano Developer Kit. Does this mean NX module can be fitted into the Nano baseboard? The answer is yes. So if you recall, a few months back, we released an update to the Jetson Nano baseboard. So we had a new version of Jetson Nano. So if you're using the newer version, which has, and the easiest way to know that is the new version has 2 camera connectors on the carrier board. So if you're using that version of Jetson Nano, then yes, you can use the Xavier NX module and put it into the Nano carrier board. Our benchmarks run only on synthetic data. The data that I showed was actually, none of the benchmarks run on synthetic data. You can run it on actual images. And we do provide some samples of doing that in some of the tutorials that I mentioned, like 2 days to a demo or the Jetson model suite. And I think we are coming to a close to the end of the session. There are a lot of unanswered questions. We'll try to get back to those and post the answers. So I would like to again thank you all for joining us today. I hope you enjoyed it and learned something, and continue to attend the other sessions for the CTSA Digital.